Hello everyone, welcome back to Physical Geology 1403. Today is lecture 9. Gavin, would you grab the door for me real quick? Thank you. Before we jump in, I want to open up the floor to anyone that has questions or comments or any cool, interesting science stories you may have heard about. Yeah?
Could I ask you a question that's not related to it?
A question that's not related to geology? I mean, sure.
All right, so is boba tea your favorite?
Boba tea is like one of my favorite drinks, yes. Now, I don't drink tea. So the boba teas I get are the milky teas that don't actually have any tea in them. But those are really good. I love milky boba teas.
What are your favorite toppings?
I like having lychee gel in there. And my favorite, gosh, it would either be honeydew or mango for the flavor. Yeah. Boba. It's a milky boba tea. So it's essentially milk with some like fruit flavoring, like strawberry, mango, coconut, honeydew, whatever you order. And then they put the little gel capsules in there, right? So I like having the little squares of lychee jello in there. They're really yummy. You guys ever had lychee? Oh, okay. You got to go to the Oriental Market on Andrews Highway. No. Well, maybe like tiny dragon fruit without those spikes, right? They kind of, it's a shelled fruit, but when you pop it open, it looks like an eyeball on the inside. And then you pop it in your mouth, and you can eat the flesh off of the seed in the middle. It's really yummy. But you can go to the Oriental Market, and you can buy cans of lychee fruit, and they're really, really good. Highly recommend. Very unique flavor. Yeah.
Can you count to 10 slowly?
Can I count to 10 slowly? Are you mocking me because of how fast I talk?
No, he just wants you to count to 10 slowly.
Okay, hold on. I am so skeptical of this right now. I feel like you're going to catch me in some kind of D's nuts joke or something. How are you going to turn this on me?
I'm just counting to 10.
Should I do this?
No.
I don't know if I trust you guys that much.
It's just counting to 10.
Should I do this?
Well, I don't know what they're doing.
I don't know either. Do you guys know if this is like going to come back on me?
Honestly, just go.
1, 2, 3, 4, 5, 6,
Wait, no,
7.
stop. You're going to do 6.
I don't know what that is. See, this is what I ask you guys. What is this?
It's literally whenever they just go 6, 7, 10.
What is that?
Just 6, 7.
What the heck is a 6-7 joke?
Some kid said it now to me.
I have the video if you want to.
Is it rude or mean? Does it mean anything other than just being dumb humor? It's just dumb. It's just brain rot. 6, 7, 8, 9, 10. There. How about that? All right. Not really. We're in class. But thank you. Maybe later. All right. What?
Like doing this with your hand.
Yes, I can do that, but I'm not going to do that. I already said yes to one request. That's all you get for today, okay? One brainless request. All right? Tomorrow then. Tuesday we meet again. All right. Any interesting questions or comments or stories?
Last Tuesday, whenever you went over gravity,
Yes.
that actually kind of helped me in my physics class because I had physics 10 period.
Yeah.
So like I end up the day with physics, and we were going over gravity, and I was like, oh, I'm an expert already. So I'm using my geology notes for physics.
And they helped you do well on the assignment?
Yeah, because it taught me. What really helped me was that the greater the mass, the stronger the gravity is.
Yeah.
So that really helped me.
That's great. I love hearing that. Yeah, guys, I mean, I'm teaching you concepts related to geology, but what have I told you before? Geology is essentially physics and chemistry and biology all mashed up together. So yeah, the things that you learn in here are relevant in pretty much any other science class you're going to take in this degree and any ones you pursue afterward. Right? I love that application. Thank you so much for bringing that up. It helped him in his physics class assignment after we had our conversation about gravity last time. Speaking of gravity, I've got a cool story if you guys want to hear it.
We do.
Great. All right. So There is a project going on right now to build a device, or actually several devices, in space. This project is called LISA. It's an acronym, and I really don't remember what the actual, I think it's laser interferometer something, okay? But it's a device called LISA. It's going to be 3 satellites that are put in orbit of the sun. So it'll be a heliocentric orbit. Okay, so essentially, let me draw this out for you. This is our sun right there. The satellites are going to be here, here, and here. And let's say that, Earth is orbiting something like that, right? So these satellites are going to be in orbit of the sun, and their whole purpose is to collect photons, light, that enters into one. A light photon coming from this direction will enter into here and pass through that collector, and then sometime later pass through that collector. And it's going to be able to measure the effects of gravity on these photons because of the amount of time it takes for that light to go from one to the other. And because there are 3, they'll be able to collect these photons traveling from any direction, going through at least 2 of these at any given time. Photons don't have that much energy. Oh, are you asking about the sun? No. They're millions of miles from the sun.
Oh.
Yeah. Okay, they're really, the size of the sun here is kind of exaggerated. Okay, they're really, really far from the sun, and they're taking into account the radiation from the sun. They have a kind of a shield around these things specifically to deflect the radiation from the sun and the influence it would have on these devices. But the whole point is they are absorbing these photons, these light particles, waves, however you want to think of them, from all around our galaxy, and they can see what the influence of gravity is on these things. And using these devices, they will be able to identify all of the strongest gravitational forces in our galaxy. Black holes, dark stars, neutron stars, pulsars, stuff like that. All of these incredible stellar bodies that we can only barely see with our telescopes, we will be able to know exactly where they are, how far away they are, and their gravitational forces by using this device. Now, that sounds intellectually interesting, but what practical effect does this have? Let me ask you this. How do you navigate in space? Well, it's really hard. How do we navigate on Earth? What do you use? A GPS system of some kind. GPS systems are based upon satellite telemetry of the surface. You have to map the surface for the satellite telemetry to be accurate, right? How do you do that in a massive 3-dimensional space like space? You need to have points of reference. And how do we get accurate points of reference? Nothing in our universe travels faster than the effects of light and gravity. So once we can identify a map of all of the gravitational bodies around our solar system, we can theoretically make a, for lack of a better term, GPS system that can tell us exactly, we can use for directional guidance anywhere in our solar system and beyond that. It's pretty awesome, yeah.
So how long would it take for those satellites to get to the sun?
This mission is being launched in 2035. The principal pusher for this is the ESA, the European Space Agency. NASA, up until this year, was a partner, but their funding, our illustrious leaders in Washington, pulled all of the funding for the project, which means that the United States is no longer contributing to the project, which means that if that continues, then the European Space Agency will carry on without us. And the United States won't have any part in the success of this venture, which would be a ridiculous crying shame. So if, like me, you think that this is a worthy endeavor, there is a website, I think it's called savelisa.org or something like that. You can go and you can actually find out how to petition our local government leaders in Congress to push for the funding to be given back to this. I strongly urge all of you to do it. I've done it. This is an incredible boundary-pushing project that should not be allowed to die, or at least it's not going to die. We're just going to get left behind. Can you donate? I don't think they're accepting donations. But the whole point of this website is to teach you how you, as a citizen of the United States, can advocate for something you strongly believe in. And if enough people in the community tell their government leaders, like our congressmen or senators, hey, this is something that we should be part of, then they can take that to Congress and the Senate and try and get that funding reinstated. So I'm just trying to do my part by sharing that. And I mean, if you would be so kind, because this is what's going to happen, guys. If the United States gets left behind scientifically because we pull all the funding, we will never catch back up. Never. We've already pulled so much funding from military development, China has left us in the dust. It's not public knowledge. They have submarines we can't detect. They literally show up off the coast of California, and we had no idea they were there. They get past all our Pacific fleets, It doesn't even matter. We have no idea. We don't know what technology they're using to do it, right? They send probes and drones over the United States, and we don't know it's there until some citizen sees it. It gets past all our detection devices, right? So we've already fallen behind in far too many ways. We really, really, really cannot afford to fall behind in space technology because we'll be left out of the party. We will cease to be a powerhouse technologically. And I'm not advocating for an American empire. Please don't get me wrong there. I'm advocating for us to be part of the party, to be in the room. Yeah. Elon Musk is trying to go to Mars mostly for ego. Oof, I just made some enemies who watch this on YouTube by saying that. I admire Musk for his entrepreneurial spirit, but I think that he wants to have someone on Mars, and maybe he even wants to be on Mars so badly in his lifetime that he's willing to skip steps, and you can't do that in good science. The right way to do this is we develop the moon. We develop the moon, all of a sudden, the cost and time it takes to get to Mars plummets. We spend 20 to 30 more years working on moon development and building facilities up there and manufacturing ship pieces here, putting them up there, assembling ships up there, all of that. We spend a few more decades trying to do that collectively together. And we get to Mars super easy because we already know how to do it. We've done it on the moon. He wants to go straight from Earth to Mars, which, we should explore Mars, but sending men permanently up there, not practical. The amount of time and money it takes to send a ship from Earth to Mars is incredible. The amount of time and money it would take to send from the moon to Mars, easily 10 times cheaper. Easily. Why? Because you don't have to fight the gravity and atmosphere of Earth to get away from the moon. Right? Think of all the fuel it takes to break away from our orbit and to get out of our atmosphere. That's why we have those massive booster engines on all our rockets. You can get rid of the booster engines if you launch from the moon. So there's a right way to do it and there's a fast way to do it. And if you do it the fast way, you're more likely to make mistakes. You're more likely to have a Martian situation. You guys ever see The Martian with Matt Damon? Great movie. Fantastic book, by the way. Andy Weir, incredible author. Highly recommend. Okay? He does his research, and I love it. But something bad happened. People died, and they weren't able to get a rescue mission to him for 6 months? Because they had to scramble to find the funding and the fuel and all of the supplies and a ship that would work to launch from the Earth. Something like that is far less of a problem, still a possibility, but far less of a problem to respond to if we have active facilities ready to respond on our moon. So that's my piece. I think that he just wants to go to Mars because he wants to get there before he dies and he wants his name on Mars. So yeah.
So why doesn't he want to just go to the moon?
Because Mars is sexier than the moon. Men have been to the moon before. Doesn't matter if it's been 50 years. Men have been to the moon before. He wants to put someone on Mars for the first time and have his name attached to it. It's purely ego. That's my opinion. All right. Any other interesting questions, comments, or stories? No? Are we ready to start then? What are we making today, Juliet? A what? Another Snoopy? Is that your favorite thing to make? It's the thing you got access to. Is that what you said?
No, people ask me.
Really? Okay. So it's like your most popular item is to, and it's the knitting, right? You're knitting it? Crocheting. Okay, you're crocheting Snoopies because it's the thing people ask you most. Interesting. All right. Well, today's lecture, I'm having a super paranoid moment here. Give me a second. I pushed record, right? Yes. Oh, I've done that before. It sucks because then after you all leave, I have to come in here again and do the whole lecture again for them. It's just teaching to a camera. Yeah, that's why I'm a little paranoid about it, and I double check sometimes, okay? Because I really don't want to do that. All right, so today we are talking about glaciers and glaciation. Why are we talking about glaciers in a class about geology? Yeah.
Because last time we went over groundwater and stuff, and where like only like a small percentage of water is, you only have like a small percentage of like fresh water, and like over half of that's like in glaciers.
Yeah, way more than half of it. Right. Okay, so what he's saying is we talked about groundwater, running water. It kind of makes sense to go over frozen water next because that's part of what I was talking about. Well, there's actually a far closer reason as well. Another reason. Yeah. Okay, so we could talk about glaciers from the aspect of global warming. Global warming is a change in our environment, and environmental studies is a big component of why we utilize geology as a science. Sure, but there's another reason as well, one we've already learned about in the class. There, glaciers are ice, and ice is a mineral. Why is ice a mineral? Someone remind me what the definition of a mineral is. Okay, chemical formula is one of the things.
It's a naturally occurring inorganic solid that possesses a orderly crystalline structure
And
can be represented in a chemical form.
there it is. Okay, a naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Those 5 requirements to be a mineral. Does ice match those? Yes, it matches all of them. So, by the definition of the term, ice is in fact a mineral. Now, I'm not saying water is, right? But ice sure is. It matches those qualifications. So, glaciers, ice, mineral, geology. Here we are. All right? But first, we got to talk a little bit about some of the properties of water before we can talk about ice itself. Okay? There are some very interesting things about water. For example, water has something called cohesion. Cohesion is a property where substances, especially like substances, like to stay together. So in the case of water, hi Faith. So in the case of water, you get water molecules that like to stick with other water molecules. Have you ever been driving down the road and you notice that a raindrop falls on your windshield and stays in like a little bubble? Why does it do that? Okay. Why does it do that? Cohesion. Okay? Water likes to stick to water. Rivers run in a straight course, right? If I were to put, if I were to put a drop of oil on that glass, what would it do? Drill down? I'm not putting acid on the glass. Go down the windshield? Okay, well, let's just say it's a flat plane of glass. Let's say I've gone from a tilted windshield to a flat plane of glass. I put a drop of water on there. It stays in a bubble. What does the oil do? It spreads out as thin as it can, right? Some oils are more cohesive than others, but like say a vegetable oil, it'll spread out super thin, right? Not as cohesive as water is. Water has a very strong cohesive property, all right? Water is also very efficient at holding energy, yeah.
Is that why you can like fill a glass of water like a little bit over the top?
Yeah. When you fill up that glass of water and you're very careful, it doesn't actually spill over. You notice that it kind of bubbles up over the edge of the glass. A little bit more water and it'll tip over the edge. But yeah, that cohesive property is what makes that bubble. Good. Okay, so its energy absorption properties. It is slow to absorb heat, but also slow to let it go, at least relative to most solids. How about, okay, so there's this example I like to use. Early on in civilization, as in, honestly, from 10,000 years ago to within the last couple thousand years, most human civilizations, most human communities relied upon some sort of maritime industry, usually fishing to sustain their communities, right? Well, in that industry, typically, in your sailboats, you would ride out on the morning breeze and come back on the evening breeze. But why is there a morning breeze and an evening breeze? It has to do with the rate at which water, aka the ocean, absorbs solar energy versus the continents where people live. The continents, the landmass, will absorb water much faster than the water will, but it will also release it a lot faster than the water will. And as it is absorbing or releasing energy, it's going to affect the temperature of the air above it. So in the morning, as the sun is rising and it's, bathing both the ocean and the nearby land in heat, that continent, that landmass is going to heat up faster than the water, so you get hotter air above your landmass. Hot air moves into cold air. It makes a high pressure front that moves into the low pressure. That's what makes wind. So in the morning, when things are heating up, you get a breeze going from land out to sea, and your sailboats follow that. In the evening, as the sun is setting, the land loses heat very quickly. But the ocean, which has been heating up all day, loses it slowly, which means you get warmer air over the ocean and cooler air over the land, and you get a high front moving into a low front the other direction, and a breeze goes from the ocean back across the land. And your sailboats ride that back home with the day's catch. Okay? This is actually where the concept of our workday comes from. Traditionally, you would wake up with the sun and go to sleep with the sun, because these communities would ride that breeze out and ride that breeze back. Now we call it a 9 to 5. So usually, depending on where you are in the world, you wake up after the sun has already risen, and you finish working before the sun has set. But that's where the concept came from, okay? So it has relatively different heat absorbing properties than, say, landmass or metal, right? It takes a while for you to boil the water, but then that water stays hot for a while too, right? All right. Ice is less dense than water. How do I know that? How could I possibly test whether ice is less dense than water?
Put it in water and see if it floats.
Does ice float in water?
Yes.
Yeah, you bet it does. Right? You go to any local fast food restaurant and they'll give you ice in your drink. That drink may or may not be water, but your ice will probably float in it. Right? Why is ice less dense than water?
Does it have air
No, it doesn't have air in it. At least not usually. Someone remind me what density is.
The amount of weight an object has?
Not weight. Weight is dependent on gravity. Okay, mass is a factor of density. What's the other factor? volume. Density is a measure of mass per unit volume. So if I want to make something less dense, was that a question or a comment? Gavin, you had your hand up. Oh, you were just messing with your hair? Okay. If I want to change the density of an object, what do I do to that mass-volume relationship? There are two ways I can affect the density of an object. Increase the volume, or if I'm decreasing density in this case, or decrease the mass. I can maintain the same volume but decrease the mass, or keep the same mass but increase the volume, right? If I increase both mass and volume at the same rate, then I'm keeping the same density. Same thing if I'm decreasing both at the same rate. In this case, what's happening here, if I take, say, 1 gram of water and freeze it, is my mass changing? Is it? I still have a gram of water versus a gram of ice. I haven't added anything. So what must be changing? If my mass is remaining constant, the volume is what's changing. You good? Okay, the volume is what's changing. If I take a cup of water and freeze it, I am not changing the amount of mass in there, but that ice takes up a little bit more space because the crystalline framework that it forms is expanding and taking up a little bit more space, about 9% more space as it turns out, than the liquid water did. The crystalline framework simply takes up a little bit more volume than my loosey-goosey water molecules did when they were not frozen. So it expands by about 9%, which isn't much, but it's just enough to decrease the density, which increases the buoyancy. Boom, bada boom, ice floats on water. This is what icebergs are. Okay? Icebergs are gigantic chunks of ice floating in the ocean. Now, more iceberg is under the water than above it, just like there's more ice cube under your glass than above the water, right? About 1/7 of ice is above the water level, and the rest is typically below the water level, depending on the liquid that it's sitting in. Salt water versus fresh water, soda versus water, that sort of thing. Okay? Right. So, we've established that ice is a mineral. That's why we study it. You're going to see how it behaves very similarly to some of the things we've talked about already as well. Now, yeah?
So, like, what percentage of the iceberg is above the water?
1/7. Approximately 1/7 of icebergs are above the water. They go much deeper under the water, which is what killed the Titanic, by the way. Are you familiar with how the Titanic sank? They weren't keeping a close enough watch. They came up on an iceberg. They turned the ship at the last minute so they didn't hit the top of the iceberg, but they scraped a hole in the bottom of the ship with the part of the iceberg that was underwater. They couldn't see it. Yeah?
Yes, how much, like, percent is under the water, how much ice is under the water?
How much ice is under the water?
How much percent of ice is under the water?
Wait, you want a percent now?
No, like the fraction.
I just told you how much is above the water, so how much is under it? If 1/7 of the ice is above the water, then how much is below the water? 6/7. Thank you. All right, fractions, guys. Hey, is this another 6/7 joke? Man, jokes used to be funny. I don't know what's happening to this world. Someone does something stupid on TikTok and everyone talks about it for months. All right, moving right along. Glaciers, though, they do one thing that most rocks, most minerals really don't. They move. Glaciers moves. In what direction? Huh? Forward? Assuming that that's what direction? They move, okay, north, south, east, west, that's not what I'm asking. Ice will flow downhill. It goes downhill. Just like what? Well, yeah, gravity. Everything else, right? Gravity pushes things downhill. It doesn't push, actually, it pulls, okay? Gravity is a pulling effect, not a pushing effect, okay? It pulls things downhill, and ice is no different. Glaciers will move downhill, just like other bodies of water. This one being solid doesn't make a difference. We call this plastic movement or plastic behavior. If I use the word plastic, what do you think of? Okay, a bag. Sure, a plastic bag. What else? Turtles? Why do you think of turtles? Oh, because they're eating the plastic bags. Okay. When I say plastic, what do you specifically think about when it comes to plastic? I'm glad you're thinking about the turtles. So that fills my heart with joy. But let's stay on focus. Plastic itself. Okay?
Malleable or whatever?
Yeah, skipping ahead. Yeah. Okay, plastic. What else is plastic? Huh? Water bottles. This bottle I have in my hand, that bottle of Sprite. There's plastic in your laptops. There's plastic. This is made out of plastic. These are made out of plastic. My phone is plastic. This is made out of plastic. There's plastic in this charger. Look around at our world and tell me what around us is plastic. A lot. A heck of a lot of stuff in our world is made out of plastic, right? So what does the word plastic even mean? Plastic is not a thing. Plastic is a description. All the different things in our world that are made out of plastic are really hundreds of different chemical recipes made for specific purposes, but they all have something in common, which is why we call them plastic. They can be deformed, they can be shaped, they can be structured, they can be, Jackson, the word he said, malleable, yes. These are all materials that we can form to fill certain functions and needs. We can shape them, we can change them. That's what the word plastic means. Don't think of plastic today as a subject. Think of it as an adjective. It's a descriptive term. So when I say plastic behavior or plastic flow or plastic movement, now what do you think of? What is my ice doing? Huh? It's okay. You don't have to be embarrassed. You can say what you're thinking.
What was the question?
What is the ice doing now that you have this new understanding of plastic? If I tell you that glaciers move plastically, what does that mean? Sure, it's slow. Okay, tell me what you mean by it's malleable. You love that word today, but tell me what it means here in this context.
It's able to move around, like, it's able to go in different ways.
It's clearly moving because, it's going downhill. But the manner in which it's moving. It's not flowing like water. It's not falling downhill like rocks.
It's sliding.
Is it sliding?
Yeah.
Is that what plastic behavior is? It's just sliding over a surface? No. Plastic movement in a glacier means that it is deforming downhill, reshaping itself downhill. Yeah. Well, imagine if I had Play-Doh, right? Look at my hand, right? Is my hand perfectly flat? No. It's got little crannies, it's got nooks, it's got space between my fingers. If I took Play-Doh and I pushed it over the surface of my hand, would it simply slide over the surface? Or would it reshape itself according to the shape of my hand as it moves across that surface? Yeah, that's what glaciers are doing. They are deforming themselves over the surface that they are traveling on. Now, naturally, glaciers are really heavy, right? So they do have some scraping. There is a lot of weathering and erosion taking place here. We'll talk about that in a minute. But this is how glaciers move. They move plastically, deformationally, okay? So, a glacier is a very thick mass of ice that can take thousands to tens of thousands of years to form and can survive for a very long time. There are glaciers that have probably been around for millions of years, okay? Especially in the past. Earth has gotten ridiculously cold for literally millions of years at a time. Ice ages these days typically don't last more than 12,000 years or so, 12 to 20,000 years, okay? Way, way back then, I'm talking billions of years, there were ice ages so bad that they make what we call snowball Earth. We'll talk more about that in 1404, if you take that with me next term. But yeah, the entire planet covered in ice. Think about that, right? For millions of years. It's a lot, huh?
I said, imagine using Earth as a snowball fight.
I mean, you mean like picking up the Earth and throwing it like a snowball? Remember, it's still rock on the inside. That would hurt, right? It would be like if you painted a golf ball to look like snow and then chucked it at your friend. It's not a snowball, right? I just gave him a terrible idea. All right, so when you look at this picture of a glacier, what do you see?
I see, like, there's multiple colors and then there's like a big old black line down the middle.
Yeah, what are all these colors? What is all of this? It's not all rock, but there sure is rock. These darker colors, you're seeing a lot of rock and dust and weathered broken down material on the top of this glacier. These glaciers are constantly breaking down rocks around them, grinding them down, and then carrying the pieces downhill with them. Kind of like a conveyor belt for sediment. Okay? Now, glaciers are also an important part of the water cycle. Someone remind me about our hydrologic cycle. What is that?
Like there's percentage of like the salt water or something and then
You're talking about how much water on Earth is salt versus fresh. That's a statistic. I'm asking about the water cycle. Right. Okay, so we talked about this over here last time. Evaporation, then what? Condensation and precipitation, runoff, and then collection, and then back to the start, right? Evaporation again. Good. Okay. Well, glaciers are a component of collection, except not for liquid water, for solid water. Snow falls, makes ice. We'll talk about that whole process here in a little bit. But they are a part of that water cycle, okay? Also, an intersection with the rock cycle because they are minerals. And they're an important part of the weathering and erosion sequence, okay? About 60% of all the fresh water on Earth is in Antarctica, tied up in all of the ice on Antarctica. How crazy is that? What do you guys know about Antarctica, by the way? It's not. It's not. This is a huge misconception. Antarctica, no. Antarctica is a continent just like the rest of them. It's made out of rock. It's got volcanoes. It has earthquakes. It's got fossils. It had life on it for a very long time. It's only been stuck down there at the bottom of the planet for like, I want to say 50-something million years. Hasn't moved. And because that's a cold part of the planet, it got covered in ice. It's not all ice. There is a whole continent under there. It's just covered in ice right now. Yeah.
so what if all of it melts away? Like all of that ice just melts.
What if it all melts away? What does that mean? Well, first of all, as I give you the statistic here, if that all melted, we would see a 60 to 70 meter rise in the ocean worldwide. The United States would look like this. Okay? San Francisco Bay, huge, right? Massive. Puget Sound, totally swamped Seattle. Seattle's gone, okay? The Great Lakes have gotten a lot bigger. New York and the entire East Coast, all of Florida, the Mississippi River all the way up to Memphis, Tennessee, completely flooded. Houston and all of eastern Texas coastline there, completely flooded.
So we would be good though, right?
We'd be fine here.
Oh, then we're good.
Yeah, oh, well, as long as we're fine, it doesn't matter what happens, right? Yeah, screw the rest of everyone else. Who cares, right? No. This is what it would look like. We're on our way there. Yeah? How long would it take? That depends on the rate of the melting. And it's something we're going to talk about at the end of the lecture today. The melting's only getting faster. How long it will take, indeed, is the question. Right now, current models say that the sea levels could be 10 feet higher by around 2100. Yeah, you may. 10 feet higher means Corpus Christi is underwater. And all of those other destination islands that you like going out to, out there on the Gulf, those are all underwater. New York has water in the streets. Seattle is getting real close to having water in the streets. 10 feet? 10 feet makes a big difference. And then probably another 100 years after that, we're looking at potentially even 100 feet because it's only going to speed up. But we'll talk about that more later. Yeah?
So how much would like the ocean have to rise for like us to be?
For us,
Yeah.
there isn't enough ice in the world for it to rise high enough for us to be in danger here.
Yeah, we're good.
We are good here. But something I want to point out is think about the conditions that would cause this. Global warming, right? Climate change. The big bad that our society is arguing about all the time. Big bad. The big bad. Just terminology for the thing that no one likes to talk about, right? The big bad thing, the villain in the story, okay? What's happening to melt all the ice? Global temperatures are going up. What happens to us here if global temperatures rise? Sure, we don't flood, but what does happen to us? Yeah. Yeah. If it gets hot enough to melt all that ice, it's probably daily temperature around 120 here. You want to live here? Have you ever been to St. George, Utah?
I have not.
Hottest day of my life was in St. George, Utah, 119 degrees.
Was it hot? Like really
No, it's pretty cool.
It was extremely hot.
Would it burn to go outside?
Yeah, like you can be in shade and your skin still feels extremely hot, like you're standing in front of an oven. Yeah. Death Valley here in the U.S., Death Valley, Nevada, has the hottest temperatures ever recorded. I want to say like 127 degrees or something like that. Yeah, no, that becomes far more normal across the Midwestern United States if this happens.
So they come down here and they're feeling chilly.
People flee the coastline, and the only place they have to go is inland. Well, the inland is getting hot too, right? Think about how strained the resources get if everyone that lives on all of these coasts has to abandon those places and move inland. And we're already having a hard time with enough water and enough food. Man, we're talking a bad time, which is why a lot of scientists like myself are really trying to jumpstart preparation for this sort of stuff, okay? If we can think about this 100 years in advance and make preparations, way fewer people die as a consequence when this actually starts to become a disaster situation, right? We have the foresight now to know it's coming. We got to start planning for it. But instead, everyone's throwing their money at a brick wall of let's fix global warming. You can't fix global warming. We can stop doing the things that helped bring it around, but we can't fix it. And it's human hubris to think that we possibly could. Anyways, okay, coming back to this. Yeah, we were talking about Antarctica. I want to finish that thought, okay? Antarctica, an entire continent under there, a massive continent under all that ice. Me, who I am, I'm only thinking about the sheer number of fossils down there that help us understand the evolutionary progression of life, right? Undiscovered, unfound, forever. Human civilization has never found the fossils under there. We found a few fossils along the coastline of Antarctica, but there's a whole continent under there that's full of them. You know what other people are thinking about? That's a whole continent full of gold and precious jewels and oil. A massive continent in which no one has ever drilled for oil. That's what everyone's thinking about right now. There is an international agreement called the Antarctic Peace Treaty that prevents any organization or country from using Antarctica for any reason that everyone else doesn't agree with. Zero resource exploitation, only a few scientific expeditions every year, right? There are scientific facilities set up there to study it. But the relationship between all the nations continuously gets more and more strained as resources get more and more scarce everywhere else. That Antarctica is starting to look real good to everybody. So at what point does someone snap and say, screw the peace treaty, I need oil, right? Yeah, a lot of potential for conflict there, right? All right, okay, so that's Antarctica. Great question. So let's talk about the different types of glaciers, all right? You have valley glaciers. When I say glacier and you imagine a glacier in your head, you probably thought of something like this, okay? Where it's just a mass of ice that's flowing down a valley, right? Valley glaciers form on their own, flow down on their own. Did we have a peanut gallery there for a second? Anyways, okay, so what you're actually looking at in this picture is two valley glaciers that flowed down two separate valleys and then ended up in this same valley and combined forces, so to speak, and made one bigger glacier. Okay? This happens all the time in glaciers. We'll revisit the subject later. Okay? But this is a valley glacier. These things can go for a very, very far distance. Okay? From way up in a mountain range all the way down to the ocean, usually, is where they will terminate. Well, in this case, that's what happened here, right? They ended up here in this fjord. Okay, an ice sheet is a massive amount of ice covering some large area that is fed from a central source. Okay, there are only two ice sheets in the world right now. One is Greenland, one is Antarctica. Which one do you think is the biggest one? Antarctica. And really, I really need to push this home. It's Antarctica. Antarctica. We fall into this habit of calling Antarctica, right? Antarctica. There's a T in there. The Antarctic. Antarctica, right, is the continent. The Antarctic ice sheet, the Antarctic Ocean, but there is that T in there. Don't forget that. We tend to treat it as though it's not there all the time, okay? Antarctica has the largest ice sheet. It's fed from this central location where the most ice forms because the most snow falls, and then the glaciers, as part of this ice sheet, kind of spread out from this central place. They are fed from here in the middle. Same thing from out here in Greenland, where a lot of the ice forms around here in the North Pole area and pushes south along the continent. Okay? An ice cap is similar in concept to an ice sheet, but it is smaller. Think it covers more of a mountain range area, like an ice cap on top of, say, the Himalayan mountain range. Okay? It doesn't cover an enormous continent-sized area, just a very large geographic area. Similar in concept, centrally fed, but maybe only has a few glaciers associated with it as opposed to the hundreds that Antarctica has, right? Then you have an outlet glacier. An outlet glacier is kind of a glacier that breaks away from the rest of them. It kind of just goes off and does its own thing. Is that a stereo? I don't know. It looks like an old style like stereo. It's not. Okay. Okay, so we've got that. And then we have what are called Piedmont glaciers. A Piedmont glacier reaches some flat area, spreads out, and dumps all the sediment it carried. Huh. Does that sound familiar to anyone?
Sounds like
What is the word? Oh boy. Do you have it in your notes? That sure would be helpful if you had that in your notes. By golly. You have it in your notes? You just don't have your notes? Your computer's dead. Got it. Anyone else have it in their notes? Before Jackson can remember the word, he's going to keep thinking of that word. Anyone else have this in their notes? What does that remind you of, this behavior? Where the ice reaches a flat area, spreads out, and drops all its sediment. What else does that? A river does that. And what do we call it? Huh? Say that again louder. Mass wasting? No. It's deposition, but what do we call this? When a river reaches somewhere flat, loses its energy, and drops all of its sediment, we call that a? Or an?
Lake.
Mm-mm. What does it start with? All right, it starts with an A. It starts with A and ends with alluvial fan. Yes, it's an alluvial fan. Good. Okay. Doesn't that look like an alluvial fan? It does. How interesting. This solid water is behaving the same way that liquid water does, and still somehow staying a mineral. Very interesting. Okay? This is a Piedmont glacier. Okay? So, let's make a glacier. What do we need? What are the ingredients we need to make a glacier? Great! We need ice and water, which means we also need what? Cold temperatures. Where do we most reliably find cold temperatures? Sure, high north or high south latitudes, but where else?
Our freezers.
Our freezers, sure, but I'm not going to make a glacier in the freezer, right? Huh? Underground? No, it gets hotter the deeper you go underground, right? Geothermal gradient, huh? Higher up what? What do we call that? Elevation, altitude, right? Bingo. You need either to be in the North Pole or South Pole or high altitude. Why? Why does it get colder the higher up you go? Because you're closer to space. Further from the core, but that matters less when we're not talking about being a part of the solid rock of the Earth. We're talking about going up higher into the atmosphere, right? Good thought, though. Yeah. But hot air rises. Yeah. Hot air rises until what? Until it cools off and then it falls again. But why does it cool off? Because it gets colder the higher up we go. Why does it get hotter why does it get cooler the higher up we go? I've already heard because we're closer to space. All right, sure, but what else does that mean? There's no heat in space. I mean, that's true. Good. Thank you. Okay, that's a huge reason. The atmosphere is getting thinner. Okay? The atmosphere gets thinner. The closer you get to space, the higher up in the altitude we go. It doesn't hold as much energy, right? So the higher up you go, the colder it gets. Which means that at some point, at some elevation, at some altitude, you reach what we call the snow line. This might be important to write down. And when I say might, I mean it will be important. The snow line is the line above which snow remains year-round. Excuse me. Yeah, the snow line is the line in the atmosphere. It's imaginary. You can't see it, right? But it's the line above which snow remains year-round. It never melts no matter what time of the year it is. Below the snow line, there's melting even if it's only for one day out of the year. Above the snow line, that snow never melts. It just gets blown around. It gets shoved this way. It gets shoved that way. Okay? So we either need to be in the high north or the high south or at a high altitude to generate the conditions where you would get permanent snow. Because if my snow melts every year, it's not going to build up for hundreds of years, right? Right. So I have Mount Kilimanjaro here. It's offset from the picture. I have a picture of Mount Kilimanjaro coming up here in a second, okay? So our snow is deposited as hexagonal crystals. Have you guys ever heard that there are no snowflakes that ever look alike? I'm sorry, that's a lie. I just broke hearts there, I know. I want to say it's just under 30. I think it's 26 or 27 different shapes that snowflakes can make, which is where this myth came from, because if you take any two snowflakes and you look at them, statistically it's unlikely you're going to look at the same shape in them. But there's only about, I want to say 26 or 27 different hexagonal crystalline shapes that they can take. Okay? So there are many snowflakes that are alike. It's just unlikely that if you select any two, they would be the same ones. Okay? Now, as all these snowflakes are falling, they're collecting, and assuming we're above the snow line, you still have things like wind and whatnot. So my snow is going to get blown this way, and then it's going to get blown that way, and it's going to get shoved up in a drift over here, and then it's going to get blown this way and get shoved up in a drift over there. And as time goes on, my nice, well-formed hexagonal crystals are going to have little bits and pieces broken off of them by all this motion until you end up with huge deposits of just spherical snow ice grains. We call that firn, F-I-R-N, okay? F-I-R-N, firn. Just essentially spherical snow. And that gets compacted. As more and more firn gets shoved on top of it, it gets compacted, it gets condensed, and that's what makes that hard, often blue, glacial ice. Super compacted firn. Does this process sound familiar to anyone?
But you said, it's like whenever sedimentary rocks would be made.
Yes, exactly. The snow getting blown around and broken down, what do we call that?
Weathering and erosion.
Weathering. The erosion is the transport, right? It gets pushed somewhere. And then, it gets deposited, and then stuff gets shoved on top of it, and it gets compacted just like diagenesis, right? Just like lithification of sediments. You make a solid mass out of all of the grains that get compacted together. It's following the sedimentary process. Again, another reason why we study this in geology, right? It follows the same process. The same physics are at play here to make this glacier. Bless you. Okay. So this happens over time. It can take a very long time. As a matter of fact, I'll tell you here in a minute how long it takes or how big my glacier needs to be before it can actually start to move. But here's that picture of Mount Kilimanjaro I promised. What do you see in this picture? A giraffe. So where am I in this picture?
You're in like the plains.
I heard Africa, the Serengeti. Is that what you're looking for?
Yeah.
Out of curiosity, how many of you know what country in Africa has Mount Kilimanjaro in it?
Egypt?
Not Egypt. I mean, it was a good guess. Egypt is in Africa.
It's like with K.
Are you thinking of Kenya?
Yes.
It is not Kenya.
What is that?
T. It's not an unknown country. Yeah, Tanzania. Yeah. Tanzania. This is a picture taken from Tanzania. So what do you see on Mount Kilimanjaro? Volcano, by the way, big volcano. What do you see on there? Yeah, look at the ice and snow. Do you often think of ice and snow when I say the word Africa? No. And yet there it is. Why?
Because the elevation is high altitude past the snow line.
It's high enough that a part of it is above the snow line. Where? Right there. That strong line. Right there, where there is obviously snow, that's the snow line. Yeah.
That's not a mountain, right? It's a giant volcano.
It's a volcano. Yeah.
So it's like a super volcano.
It's not a super volcano, just a big one. Right? Yeah?
So Mount Everest is above the snow line.
Oh, yeah. Way above the snow line. Yeah. Okay, so here is hard evidence that the snow line exists even in some of the hottest places on Earth, right? You just got to go high enough. Have any of you ever flown in an airplane? Okay, those of you that have, when you're looking out the window, when you get up to high altitude, they usually level out between 30 and 35,000 feet. You get ice crystals on the outside of your window. You're above the snow line. The ice is forming there. Okay? Okay. So here we have examples of plastic flow and why we get plastic flow. The force that causes plastic flow to occur comes from weight. Now I'm using the term weight purposefully. Before, when someone would say weight, I would correct it to mass. Before, I was talking about mass. Now I'm talking about weight. Why? Because gravity matters in this conversation. I need to have enough weight to cause enough pressure on the ice at the bottom of my glacier that it will deform plastically. It won't just do it on its own. If I held an ice cube in my hand and I scraped it over my hand, it wouldn't deform like the Play-Doh would. I need to add enough pressure before it will behave that way. I need to have about, where do I have it? I could have sworn I put it's 50 meters, okay? I need to have about 50 meters. I thought I had that on the slide here. Oh, I do, right there. Yes, okay, good. I need to have at least 50 meters of ice before I have enough weight to generate the pressure necessary for the ice below that 50 meters to deform plastically. So the ice on the surface of my glacier, always brittle. It'll crack, it'll break. That's what we see, that's what we interact with. The ice underneath of that, under all of that weight, deforms plastically as it interacts with the surface. Okay? So that's what causes that. Now, before someone said that glaciers moved by sliding downhill. There is a little bit of that. We call that basal slip. This happens because oftentimes the glacier is colder than the rock it's on top of, right? Just a little bit of geothermal energy still rising up to the surface. Even if that rock is only 1 or 2 degrees hotter than that ice is, it's going to make a very thin layer of water between the ice and the rock. And every now and then, yes, the glacier, or at least a part of it, will slip a little bit downhill on that layer of water. But for the most part, the movement occurs because of plastic flow. Now, there is a part of my glacier that moves faster than the rest. Let me tell you a story here. I keep forgetting I pulled all my pens out here. Okay. In the 1800s, sheep herders would come down from the mountain valleys, this is in Europe, and say, hey, I was going to do an accent, but I won't because I need to be respectful here. No, I'm not going to do it. So, you know those big walls of ice, the glaciers? I don't know if they called them glaciers at that point in time, but the big walls of ice up there, yeah, those things move. And people down in the cities, in the low-lying cities, be like, no, that's ridiculous. Those things can't move. What are you talking about? How are those going to move? And so they went and they put flags on one of these glaciers in a straight line across it like that. Okay? Then they came back 4 years later, and they found that their flags had moved. But not only had they had moved and made a horseshoe shape. They came back 4 years after that and found that their horseshoe shape was even more exaggerated than before. First of all, the fact that the flags moved at all proved that what the sheep herders were saying, yes, these things do move, right? These walls of ice. But what does the horseshoe shape show? Never mind. I want to hear from someone over here. What does the fact that these flags made a horseshoe shape show about the rate of movement in this glacier? Yeah.
They could be like sliding back and forth.
Mm-mm. Good thought. Thank you for answering, but that's not it.
Like what formation is it?
Not what formation it's in. The rate of movement is the question. Where that's giving you too much information. Is there a difference in the rate of movement in this glacier?
Yes, there is.
Where?
On the on the original position.
Well, yeah, the flags are moving from their original position, which means that they're being carried downhill. But why aren't they in the same straight shape that they were before? In the straight line from one edge to the other. Why did they make this ever more exaggerated horseshoe shape? Hold on, I want to keep hearing from this table.
Because of how many stakes it's going.
The number of stakes doesn't have to do with it. That's an external factor for observation, not anything having to do with the factors of the glacier.
Is it the position that they're in?
I mean, yes, that's why I'm asking. Why are they in this new position? Emily, any ideas? Faith? Giselle? No? Okay, let me ask you this then. I'll put it a little bit more plainly, all right? Has the distance that this center stake traveled gone further than the distance than this one over here on the side?
Yes.
So now what does that tell you? Over 4 years, this one moved that distance. This one moved that distance. Why did the middle one go so much further over the same amount of time?
Is it because of the friction against the sides, like keep the further ones from moving farther?
Friction against the sides, keeping that ice from moving as quickly, which means that the fastest movement is in where?
The middle.
The middle. What does that sound like?
Like the river.
It's like a river, right? This glacier is moving at the same rate, following the same physics that a liquid river does. Physics is the same. It still has the same effect on solids that it does on liquids. It's just that solids are more resistant to it. Okay? This solid water is moving at the same, following the same physics and the same patterns as liquid water would, just a heck of a lot slower, right? It took 12 years to go from here to here, right? It would have taken water a lot less time. Maybe 12 seconds, right? But it's still doing the same thing. Water is fascinating. Water is so cool. I love water. Huh? You thought it was just a drink. Now how much more do you appreciate water? I mean, come on, right? Actually, water is my favorite drink. I know, a lot of people think I'm weird, but I don't like sodas, I don't like juices, I just like drinking water. Yeah?
So is bedrock actually unbreakable?
No. Are you asking that because of Minecraft?
That's why I asked it.
The guilty look on your face says yes. Bedrock absolutely is breakable. Okay? Bedrock is a term that we give to the layer of rock that forms the foundation of whatever area you're currently on. So like right now, right here, the bedrock is about 25 feet below us. It's mostly sandstones and limestones, right? Not below us. We're on the second floor of a building. 25 feet below the ground, okay? Below ground level. We've got approximately 25 feet of soils, broken rock, and caliche before you reach the first completely unbroken, still solid layer of rock. In the Permian Basin, that'll vary. It'll go anywhere from 12 to 25 feet depending on where you are, which is depending on where you are, it's a big reason why there aren't a whole lot of houses with basements around here. It's because it's so hard to, once you get down through those first layers of soil, it's difficult to break through that rock. There are places that have 100 feet of soil, right? And there are places that have 0 feet of soil, just a few inches on top of bedrock, right? Those are the places that we love going to look for fossils because you'll find them weathering out of the rock and you can chip the rock away. If you go somewhere where there's a lot of loose sediment, the fossils have usually been out of the rock for a long time. They will have started to break down and deteriorate because they're not as fresh out of the rock. So a lot of factors into that go into that. All right. Any questions about this? Yeah.
So you were talking about the fossils in Antarctic.
Antarctica, yeah.
Yeah. Like some of the melted spots, do people go and try to find?
Yeah, where the Antarctic continent is exposed, scientific expeditions do go. I've applied to a few of them, but they can only take, gosh, like 5 to 20 scientists at a time, and those spots are always in such high demand. I've never been accepted for an expedition. I hope one day I can be, but we'll see. Yeah. I'm also on a wait list to go on a trip to an island off of Greenland, but we'll see if that happens either.
Just fly over Antarctica.
Except that no flights go over there without that special permit.
Oh, you need a special permit to fly?
Yeah, it's an internationally protected continent.
I didn't know that.
You can't go without that international panel saying sure. The amount of red tape you have to go through to get to Antarctica is pretty crazy. Now, there are cruises that go near Antarctica, but no one is allowed to set foot on the continent without a special permit. Yeah.
Wait, you say you had to have a permanent step. Where is it?
On Antarctica.
Oh,
Yeah, because it's a protected continent. To keep anyone from going there and exploiting it, no one is allowed to go there without permission of everybody. So all of the nations that signed the Antarctic Peace Treaty, they have representatives and committees specifically dedicated to authorizing people that can go. So if
You have to get accepted by everybody for like those scientists.
people have to agree to let the people go, which means that they have to agree that it's a needed thing. Like if I went and I said, hey, over the last decade, a substantial amount of ice has melted away from the shelf, exposing a substantial amount of Antarctic continent that has not been studied for fossils yet. Because that is a scientific expedition, not intent on exploiting any resources there, purely for the advancement of knowledge, that would probably be accepted. But if someone said, hey, this section of this place is available now, I want to go and look for, gold or oil or something like that, to be like, no! That's a good way for people to start arguing over who gets what. We don't want that. So right now, no.
Doesn't Chile want to claim like a part of Antarctica?
They would love to. They claim Antarctica because of how close they are to it. They are the closest geographic nation to it. And so they say, hey, it's ours, right? But a lot of other people want it too because of the resources there. Yeah. Yeah. So yeah, Antarctica, tricky situation. All right, any other questions before we move on? All right. Let's talk about the glacial budget then. When I say budget, what do you think of? Money. What is a budget? Saving? Okay, saving is a part of it. A limit of how much you spend. Perfect. If I were to ask you to give me the definition of budget in one sentence, Remy, what would that be? The definition of a budget in one sentence.
When you go to the store and you can't afford something, or you can afford it, but then you tell yourself no, that you're not going to get it.
Okay, that's an example of using a budget wisely, not Remy. Remy. You need a budget to go on a trip? Sure, you're giving me an example, but a definition of the word budget in one sentence. As basic as you can make it. Doesn't have to be flowery or specific or scientific. What do you do with the money? So you're receiving money, and the trick with a budget is what? Limit the amount you want to spend. So ideally, you would be spending less than you bring in. Okay, so let's say a good definition for a budget is more in, less out. Okay, that's a budget. Doesn't matter if it's applying to money or not, to anything. Okay? More in, less out. If you're not living on a budget now, you sure as heck will one day, because let me tell you, adulthood is not fun. Okay? Not when it comes to money. Okay? Doesn't matter how much money you make, they always come for it. Okay? So the ideal situation is you are bringing more money in and spending less of it, and yes, so you save some, and there's rainy days. What do I mean by that? Well, maybe someone hits your car in the parking lot, right? And then drives away, and insurance isn't a factor here. You have to pay for it. Maybe you don't even have insurance because times are tough, right? Maybe you fall down and break your leg. You have to pay a medical copay. You got to have at least $500 or $600 on hand to cover that, right? There's any number of things. Every time I have to replace a windshield, I have to pay $500 out of pocket. Because the whole cost of the windshield is a couple thousand, and insurance has to have me cover some of it, right? Things in life are expensive, so yes, we live on a budget if we are wise. Glaciers also have a budget, but do you think they care about money? No. What do you think a glacier budgets? Well, it doesn't consciously do anything. But the glacial budget, what do you think that concerns? What input does the glacier have, huh?
Water that melts.
Ice, which comes from
Snow.
snow. Snow input versus melting. Bingo. That balance makes the glacial budget. Okay? So we have a region of our glacier, which we call the zone of accumulation. This is above the snow line. Okay? Zone of accumulation above the snow line. Remember, the snow line is the line above which snow can remain year-round. So, for snow to remain year-round and become incorporated into our glacier, it has to be above that line. Zone of accumulation. Below the snow line, which means that there is potential to lose that ice, we call that the zone of wastage. I think I just broke my pen. I'm a little hard on my pens. All right, zone of accumulation above the snow line, zone of wastage below the snow line. Anything can happen down here. Melting. Chunks can fall off. We call that calving. That's how glaciers are made. Chunks fall off the front of a glacier and into the ocean. Yeah.
I'm assuming that the stuff below the snow line can melt, causing the stuff above the snow line to come falling or sliding or kind of like going down to the.
Sounds like what you're saying is as stuff melts below the snow line, it makes space for the stuff above the snow line to come down?
Yes.
That's not exactly how it works, but I'm getting to that motion and how we transition downhill, okay? I'm getting there, okay? So, a good, balanced glacial budget is one where you at least receive as much snow as is lost in ice down here, right? Melting rates down here equals accumulation up there. Because like what you were just saying, stuff's going to keep going downhill. Now, I don't have to lose stuff in the zone of wastage for the zone of accumulation to continually be supplying ice downhill. A negative glacial budget is when I lose more down here than I gain up here. What's the front of my glacier going to be doing? If I'm melting stuff at the front of my glacier faster than the back of my glacier is replacing it, where is my front going to go? Huh? It's going to go downhill even though I'm not receiving as much up here as I'm losing down here. I'm melting this thing, and I'm not receiving as much from the uphill zone of accumulation. So my front of my glacier is going to move backwards. I don't have as much down here as I should. And so the front of my glacier is going to move backwards, aka back uphill. Now let me be specific here. The glacier isn't pulling itself uphill. That's not physically possible. It can't make that choice, and that would be against the laws of gravity. But it's melting faster at the bottom than the top is growing, which means that the front of my glacier is gradually going to be moving uphill. Are you following this? Yeah? No? Yes? No? Let's put it in another term. Let's say that I had a 20-foot long Subway sandwich and Jackson was really hungry. Okay? Let's say that I was pushing that sandwich towards Jackson's mouth at, I don't know, what would you say? An inch a minute. But he's eating it at about 4 inches a minute. He is going to have caught up to the end of the sandwich long before the end of the sandwich reaches his mouth this way. Right? We're doing this. Same thing's happening here. Mouth, sandwich, me pushing it. You understand that more now? Great. The front of my glacier is moving uphill as Jackson is eating it. Okay? Okay, we call that a retreating glacier. Again, not because the glacier itself is pulling uphill. The front of it is melting uphill because it's going faster than the glacier can keep up with. In an advancing glacier, the opposite is happening. The accumulation up here is happening faster than the melting down here. And so where does the front of my glacier go? Downhill. Yes. That's an advancing glacier. That's the difference between an advancing and a retreating glacier. It all has to do with that budget and how balanced it is. What can determine whether or not we have more wastage, more melting or not? Yeah.
How high, what percentage of the glacier is above the snow line?
Regardless of how much is above the snow line, this has to do with the zone of wastage because we're talking about melting. Yeah.
So how many bones do snakes have?
I want to finish answering this question first. Okay. What determines whether or not my glacier is advancing or retreating? Aaliyah, what do you think? How large it is? Sure, the mass of the glacier, if it's a larger glacier, it might melt slower because of how much ice there is. But that's not what I'm looking for here. The biggest overall influencer on how much melting happens down here. What do you think? You want to phone a friend? Okay, who do you want to help you out?
Can you repeat the question for me one more time, please?
You have chosen poorly. No, I'm just kidding. What is the biggest factor that influences how much melting and wastage we have down here?
Like the angle and like the heat.
The what?
The heat
Which has to do with?
global warming.
Yes, how hot our world is right now, how hot the atmosphere is, and how hot is it getting. Is our world getting hotter? Yes, common knowledge. No one argues that now. It's well known, well documented. Anyone that argues that we are in a global warming phase is an idiot and they don't understand science. Now, there are a lot of misconceptions about the cause of global warming and all of that, which I'll get to in a minute, okay? But we are absolutely in a warming phase, which means that more glaciers in the world are melting, which means that they are advancing or retreating.
Retreating.
No, they're retreating. Why? Because there's more melting happening now than before.
So the front's going uphill.
Yeah, the front is moving uphill. We are losing our glaciers right now because of this. Okay? So let's talk about the influence of glacial erosion. Glaciers are massive forces of both weathering and erosion. Millions and millions of tons of ice scraping over rock, crushing it, pulverizing it, turning it into what we call rock flour. It is so fine. It has the consistency of flour. It's been pulverized. Okay? We call that rock flour. You'll also get these things called erratics. What's this rock doing out here? What? Yeah, what? How? Yeah, it's just chilling. How to get there? It doesn't look like anything around it. It's in the middle of a field. How to get in the middle of a field? The nearest mountain's all the way over there. Did it fall off that mountain and then roll over that hill and then roll up this hill and then end up here?
It was like probably being moved on like by a glacier, and that glacier melted.
Yeah.
The rock settled right there.
Exactly. Some time ago, a glacier moved down this valley that had that rock in it or on it. That glacier melted there and dumped that rock sitting here in the middle of this field. We call that a glacial erratic. When I lived in Ohio, I was not far from a park that had an enormous house-sized chunk of granite sitting in the parking lot. Okay? There's no granite in Ohio. Nearest granite's up in Canada. How'd that chunk get there? It was carried down by glaciers from Canada and dumped there in the middle of Ohio. Okay? Glacial erratic, that's what that is. Abrasion is what we call it when the glacier is scraping rocks over the surface of whatever it's on top of, and you get these stripes, these striations, these channels that are carved into that surface by the rocks that the glacier is scraping over that surface. Okay? And then I already told you calving is when a piece of ice falls off the front of the glacier and into the water and makes an iceberg. So real quick, right here. I'm going to explain to you some of the parts of glacial geography. Okay? Oh, camera. Hello. Right here. Hi. There we go. All right, so glaciers. We have your valleys, okay, like this. Each one of these is a glacial valley. Okay, well, these main ones, these are glacial valleys. Then we have what are called cirques, C-I-R-Q-U-E-S. Okay, cirques. That's these sort of side tributary kind of glaciers here that feed into the main valleys. Okay? And then we've got these ridges between the valleys. We call those arêtes. Okay? They're very sharp, very razor sharp because they've been scraped so much by the passage of all this ice. And then where multiple arêtes come and meet together, they make what's called a horn. Okay? So you get your arêtes and your horns. And then fjords. You ever heard the term fjord before? Fjord, it's a Norwegian word. No? Okay. A fjord is what happens when your ice age is over, your ice has melted. What does your ocean do? Why? Why does the ocean get higher? Where's that melting ice going to go? The oceans. Ocean levels rise in periods of global warming and fall in ice ages, in glacial cycles. Okay? So in a glacial cycle, when my glaciers have formed all of these valleys and carved their way down to sea level, then it ends, all that ice is gone, all of that water has gone back into the ocean, ocean levels rise and flood, or at least partially flood, my glacial valley. Okay? Sea levels up here, filling up my valley. This is a fjord. A fjord is a drowned glacial valley. It's been flooded by the ocean. Okay? There are tons of fjords in Norway and those other countries up there in Northern Europe. Matter of fact, during World War II, a lot of German submarines would hide in the fjords, and there were so many up there that it would be almost impossible to find them once they got in there. Okay. Then we have Roches Montagnaises, which I apologize, I am not fluent in French. Matter of fact, it's about the only French I know. But this is what happens when you get a hill that has the misfortune of being in the way of a glacier. Okay, so that glacier runs into this hill or other upraised geologic area, okay, formation. It runs into it and kind of scrapes one side of it flat into a ramp as it shoves itself over that surface and then kind of falls down the other side. And it keeps shoving itself up over here and down the other side. So you get this sort of wedge shape as our ice is going over it. Okay, these are helpful because we can see what direction the glaciers came from by finding these. Like, oh, okay, so it's a wedge pointing that way. It came from that direction, right? Glacial drift is a term used for the sediment that is moved by all of this, or crushed into sediment, rock that's crushed into sediment by these glaciers, by their movement, by their power, by their energy, okay? And we get deposits of this sediment wherever the glaciers are currently melting. Now, drift is a term that you'll see in some literature. You'll also see the word till. I kind of prefer the word till. Drift is, I don't know, it has some implications for the motion of how it got there that I don't necessarily want to confuse you with. I prefer glacial till as a term. And as a matter of fact, you've already come into contact with rock made from this sediment. In Lab 3, hopefully you guys have been working on Lab 3, there is a rock in there that is made out of this glacial till, okay? Stratified drift or stratified till is when you get layer upon layer upon layer upon layer of sediment that corresponds to melting seasons of your glacier. So if I get one layer that corresponds to, summer of one year, and then another layer that corresponds to the summer of another year, these are stratifications, okay? They're different layers. And we can use those to calculate how many melting seasons different glaciers had in one particular area. It was sitting here for 100 years before it moved backward and started depositing sediment here. And then 50 years later, it moved backward again and was depositing sediment there. Stuff like that. All right, so for moraines. Moraines are what we call the deposits of sediment that are in or on our glacier. So there are several different kinds. As our glacier is scraping material off the side of the valley, okay, so here, scraping material off the sides of the valley, that material, that rock, that sediment, travels down on top of the glacier along the sides. We call those lateral moraines. Okay, these sediment belts that are on the sides of our glaciers. Okay, lateral moraines. A medial moraine is where two glaciers meet up and their lateral moraines combine into one medial moraine that's now in the middle of this combined glacier. So it's going like this. And now we have a medial moraine down here. You can see that in this picture. Look, here's a lateral moraine. Here's a lateral moraine. The two glaciers have met up, and now this medial moraine is continuing downhill. Same thing here. Lateral moraine, making this medial moraine right here. This medial moraine is fed by the sediment from those lateral moraines, continually being generated as the ice melts downhill or moves downhill. Then we have a terminal moraine. Terminal moraines are wherever your sediment is being deposited at the base of your glacier. Okay, so right here, glacier is right here. Its terminus is right there, the end of it, the front. And this is the terminal moraine that is being deposited there by all that melting ice. It kind of helps if you think of this glacier as a conveyor belt for all the sediment moving downhill. It's dumping the sediment there at the bottom. All right, so looking at a more broad view, ice ages. Yeah, of course. Ice ages, glacial cycles. Why do these happen? How do they happen? What effect do they have? Well, a glacial cycle happens when Earth's temperature cools to the point that our snow line falls. Why would my snow line fall? Global temperatures are cooler, which means you have to be at less high altitudes to have snow year-round, right? If my global snow line falls, that means that more mountains and higher elevation zones on continents can have snow year-round. More snow year-round means more glaciers forming. More glaciers forming! What does that do? Have you ever heard of what is called a positive feedback loop? A positive feedback loop is a self-sustaining system, one where one aspect of that system creates an effect that is positively reinforced by the later on cycles of that system. So in this case, ice is white, correct? It reflects energy. It reflects heat. The more ice we have on Earth, the more energy is reflected back into space, and therefore cannot be absorbed by Earth. We absorb less energy, we get less heat. Less heat, lower temperatures. Lower temperatures, more ice. More ice, more reflected energy. More reflected energy, less heat. Positive feedback loop. So as more and more of Earth cools off, more and more ice is forming, spreading from the north and the south and the highlands. More ice reflects energy, and we enter an ice age or a glacial cycle, depending on how severe it is. Okay? Technically speaking, an ice age is a period in Earth's history when there is ice at both poles. So, again, technically speaking, we are still in an ice age because we have ice at the north and the south. We're moving out of it. What we recently came out of about 12,000 years ago was a glacial cycle where that ice had moved really far south and really far north. We left that about 12,000 years ago. The ice has been melting for 12,000 years. We are on our way out of this ice age. As soon as that ice is gone, or this ice is gone, we will no longer be in one. Okay? We are in a global warming phase, but still technically in an ice age. Okay? Yeah?
So how long until that ice starts like coming back?
Well, that's the question. It's a good question. I'll talk about that in a minute. Okay? So that's a positive feedback loop. What are the effects of ice ages and glacial cycles, though? First of all, there are extinctions. There are some things that cannot adapt fast enough, a lot of things, that cannot adapt fast enough to survive drastic climate change. We're seeing that right now. There's a massive extinction occurring right now for things that cannot adapt to our warming temperatures fast enough, as well as the gases we put in the atmosphere, the increasing acidity of the ocean, things like that. There are dozens and dozens of species of both plants, animals, and insects that go extinct every day, okay, because of the condition that's going on right now, okay? If we were to enter another ice age, and actually this is what Earth looked like 12,000 years ago, okay? 18,000 years ago during the height of that glacial cycle, okay? It ended about 12,000 years ago. This is what the United States would have looked like. Compare this in your head to what I showed you about what I showed you the map of if all of the Antarctic ice melted, right? Look how much bigger and thicker our east coast is. Florida and the Bahamas are actually connected at different points during this glacial cycle. In this picture they're not, but they were, okay? Mexico, much bigger. Baja, California, much bigger. There is no San Francisco Bay. There is no Puget Sound. There is no Chesapeake Bay. There's none of that. There is no Great Lakes. It's covered in ice, okay? This is what it would have looked like 18,000 years ago. As a matter of fact, you can take a boat out here to the middle of the Gulf of Mexico, well, not the middle, but way out into the Gulf of Mexico. You can drill down in the sediment there and pull up fossils of land animals from 18,000 years ago, because this was all solid land. There were animals living out here in what is now deep Gulf of Mexico water. Okay? Okay, so what causes ice ages and glacial cycles? Well, the oldest known repetitive glacial cycle is about 2 billion years old. So obviously, the sequence of warming and cooling and warming and cooling and warming and cooling is nothing new to our planet. Okay? First of all, you're probably sick of hearing me say this. Tectonics, right? So much of this stuff I teach you comes down to tectonics. Why would, Tectonics are in everything, yeah. Why would tectonics make a difference as to whether or not I make glaciers? Well, yeah, the movement, but in what respect? As these plates move, they interact with each other. One way they interact, yeah, what are you doing right now? Convergent plate boundaries make what? Mountains. And those mountains do what? Go above the snow line, which means we can form glaciers. More glaciers, cooler temperatures as we reflect more energy. Plate tectonics plays a role in this. Okay? Also, there are these things called Milankovitch cycles. I put my globe away too early. Milankovitch cycles are the rate at which the Earth moves around our sun in a couple of different ways, okay? So first of all, we've got eccentricity. The eccentricity is the plane or the shape of our orbit around the sun. It is not perfectly circular. Did you know that? We don't orbit the sun in a perfect circle. We have an eccentric circle. It's more like an oval. So every 100,000 years, we are at the exact same position that we were 100,000 years before, which I'll get to in a second. How often do we orbit the sun? Once a year, right? Okay, that's what defines a year. But every 100,000 years, we end up in a very special, specific circumstance, okay, where we are in the exact same position relative to the other ways that we orbit the sun. Next up, obliquity, okay? The obliquity is on a cycle of about 41,000 years, and that has to do with the axis of the Earth versus the plane of our orbit. Have you ever wondered why the globe is tilted like that? Why aren't globes like this? Yeah, the axis of our orbit is not the same as our orbit around the sun. Okay? We are currently doing this. At that angle, relative to the angle of our sun, we are orbiting the sun like that. Okay? That's why the equator is at this angle. The equator represents the side of our planet, or the position of wherever the sun is directly pointed at our planet at any given time. Okay? So we're orbiting the sun like this, but at an angle relative to our plane of orbit. Okay? That's our obliquity. Then we have our precession, which is our wobble around that axis. Earth is doing this at the same time. At the same time that it's doing this, at the same time it's doing this around the sun. Boy, don't you feel dizzy just thinking about it? Okay? Milankovitch cycles describe the rate at which we travel along all of these different motions, and at the right times, certain parts of the Earth are pointed at the sun, as we are also the furthest from the sun. The further we are from the sun, the less energy we absorb already. But what if the Pacific Ocean and a big chunk of Antarctica was pointed at the sun at the same time? We already learned today, water absorbs energy very slowly. Ice reflects it. So if on this cycle, we end up with this side of our planet facing the sun at just the wrong time, I say the wrong time, it's mathematical, that's why we have these dates, okay? We end up with a cycle of, for that brief period of time, Earth doesn't absorb as much energy, and that positive feedback loop begins. Earth gets cooler for one season, that's all it takes. Glaciers start to grow more as the snow line drops. More glaciers, more reflected heat. Even as we're moving closer to the sun again, we have too many glaciers now. We still can't absorb as much heat as before. The positive feedback loop continues. We enter an ice age. Okay? Then there's the atmospheric component. Greenhouse gases. Have you ever heard of greenhouse gases? Yeah? What's the most common greenhouse gas you've probably heard of? Carbon dioxide, perfect. There are many others, methane being one. Okay, there are lots of greenhouse gases. Generally speaking, greenhouse gases are gases which are large enough. They're a large enough molecule that either radiation will simply bounce off of it in the atmosphere, or as that radiation impacts our planet, goes through the greenhouse gases in our atmosphere, it interacts with those larger molecules, loses a lot of its energy, and can't escape the planet again. So the more greenhouse gases we have in our atmosphere, the more heat gets trapped on Earth, increasing temperatures. And this starts the global warming positive feedback loop. More greenhouse gases in the atmosphere, hotter planet. Now, this takes me to the conversation of, well then, did we cause global warming? How many greenhouse gases have we pumped in the atmosphere? A heck of a lot. So much. Way more than would naturally be there under any other circumstances had we not. But there's a kicker here. The Earth started heating up almost 12,000 years ago, guys. Way before we started burning anything other than wood. Way before coal, way before oil, way before natural gas. Way before we started putting this much carbon dioxide in the atmosphere, Earth was already heating up. So, what that does say is we are not responsible for the start of global warming. But what we know now is we are most certainly responsible for how severe it's going to be. Did we know it was going to happen? No, we had no idea what we were doing. Now we do. And the impetus is on us to try and make a difference. Now again, I'm going to repeat what I said before. Pandora's box is opened. The genie's out of the bottle. You can't shove it back in. We can't take billions of tons of carbon dioxide out of the atmosphere, no matter what kind of technology we build to do it. And we don't have the kind of time or money to even make something that could do that, to make a mechanism to do that. Before we even could do that, the catastrophes will have happened, which is why myself and many other scientists, a growing number of us, are of the opinion that money should stop getting thrown at a wall like fix global warming and more towards let's focus on surviving it. You asked a question a little while ago, I think it was Jackson, when will the next ice age be? It's a good question. Whenever Earth decides to recover from us. Okay? Whenever we can get out of this positive feedback loop, and it's something that Earth is going to have to do on its own, okay, that's when we'll go into another ice age. Could be 20,000 years, could be 40,000 years, could be 100,000 years. I don't know. But what we need to do is focus on being responsible stewards for our planet again and figuring out how to keep the human civilization alive at the same time. Okay? Can't fix it. Survive it and do better for the future is where I'm campaigning here. Politicians will never ever say anything like that. The dishonest ones won't anyway. Okay? What do they like to say? I have the answer. I know how to fix it. Vote for me. I will make the world better. They have no idea what they're talking about because they don't know science and they hate math. All politicians hate math because math proves them wrong. Okay? Just bear that in mind. Don't get suckered in. Keep that critical thinking muscle that you are learning here in college alive. Okay? Actually use the knowledge that we give you to discern what is right, wrong, true, false, and what deserves more thought. Okay? Any questions for me today? Okay. Well, then that's all I've got for you. You have all 4 labs assigned, so you should just be able to jump straight into whichever one you're currently on. If you have any labs you're done with, please stack them on the end of the table. Ask me for the new ones, and I'll get those to you. For my online students, please let me know if you have any questions. You can leave comments on this video in the YouTube, or you can send me an email. Thank you.